Good morning, everyone. It is shortly past 8, so I think we're going to start. I hope that everybody can hear me well.
Sure.
Good, great.
But morning is an exaggeration. It's 5 here in Europe.
Oh yeah, I'm sorry. It is 8 a.m. I am in California right now, so you can all be very jealous. It's gonna be 30 degrees Celsius today. I I personally got sick of the heat, but yeah. So good morning or good afternoon to everyone. I'm really happy that you're joining me here today for an advanced workshop of BiofilmQ. So I'll go up ahead and give a brief overview of, I don't know which screen you're seeing right now. You should see, do you see a presentation? Yes, you see a presentation. That's great. I want to start by giving you a brief overview of what we're going to look at today. So we have a few different topics, and I hope that we can get through all of them today. The first one is that I want to talk a little bit more about merging. So merging is something that was discussed in one or two previous workshops, I think already. So there is something on YouTube that you could watch to also go a little bit more into depth beyond what we're going to do today. But what I found is that it's a method that not a lot of people use when they use BiofilmQ. It's not like, it's sort of a little bit hidden, but it's quite useful for different purposes. So we are going to talk about that today. Then we're going to talk about custom properties, where we have one version where you use and need MATLAB in order to perform it. Otherwise, we also have an option to implement custom properties without needing to go into MATLAB and program. We're going to talk a little bit more about some of the visualization features. And finally, I hope that I can show you a little bit of batch processing, mainly walking you through where you can find it, because I think it's also a little bit hidden, and how to use it. So that, since this is an advanced workshop, I do hope that you have at least a little bit of experience with BiofilmQ. You have a rough idea what it does, or maybe attended some of the previous workshops by Eva and Niklas, which were really great over the past 2 days. If that is not the case, you can still follow along and then catch up later on by watching some of the tutorials, and maybe I can show you where to find them. So do you see the Firefox screen right now? Or do you still see this presentation? Okay, Eva's nodding. So if you just type BiofilmQ into YouTube, you will find that we have this tutorial series here, which is probably the best place to start. And it's basically just a summary of a lot of tutorials that we have. It starts with a presentation that I gave a while ago. And then all the way at the end, what you can find is recordings of previous workshops. And you can see we have the I2K, this is 2020, 2022 from last year. And then today's workshop is also going to go on there. So this is where you can sort of get started if you don't have much experience with BiofilmQ yet, or you want to look at some specifics of it. We have a lot of different tutorials for a lot of different features. So this is really a good place to start, aside from, of course, the documentation, which is also quite useful. So yeah, I will start by talking about merging. So merging in BiofilmQ is something that you perform after having segmented your channels. So merging basically means that you take the information from several channels and place it into the segmentation of one channel. So in principle, you would just sort of ignore which color the signal came from. You would just say, if any pixel is assigned to a cell, either in channel 1, 2, 3, 4, whatever, I want to assign it to a cell in sort of my merged version. And we will see in a moment what this looks like in reality, basically. This means that you need to have a segmentation to perform merging. But the segmentation is basically combined from several channels. So there are, in my view, there are basically two cases where it makes sense to perform merging. The first one is if you don't have a constitutive reporter. If your data is basically spread across different channels, and that is not a single channel in which you could segment all of your cells, but you need to combine the information of several channels in order to get segmentation of the full biofilm or the full system that you're looking at. But this is, of course, only the case if you don't have an external segmentation that you import. If you already have a perfect segmentation to import that includes all of the information you want, you wouldn't need to merge because you already have that. And we will see in a moment also what I mean by this. There's no single channel in which all cells are present. The second case is, and this is probably more relevant for most of you, is that there is meaningful information contained in biomass abundance ratio overlap, sometimes also in its spatial distribution. So merging allows you to tell which channel is basically, or which cell is fluorescent and which channel where in the biofilm. So you can have sort of like a map if you have a biofilm where you have a certain type of cells that are present at the top of the biofilm compared to the bottom or on the inner versus the outer area. This is exactly what you could measure with merging. So merging is always good if you want to look at the spatial distribution of different strains of bacteria that are fluorescent in different colors. So I will now move to BiofilmQ to continue. So I'm going to look at this screen. So I already brought up BiofilmQ, and this is the data set that we are going to work with mainly today. This data set is one that you can download from the website. And just to show you here, this is sort of the ND2 file where it originally comes from. When you have a data set or when you have an ND2 file, you can import it into BiofilmQ. And I think we haven't shown this in the previous two workshops. For time, I also won't show it in detail today. I'll just show you what happens if I just select this folder here as sort of my main folder, where you have this ND2 file, so that you can see what it would look like if you were to import this from there. But we do also have a tutorial for that for more details. So when you have an ND2 file, or actually it can be any kind of file that directly comes from the microscope that is not in TIFF format, and here you can see some of the other file types that are supported. You can see we don't have an image shown here because BiofilmQ doesn't yet know basically what the images look like, but what BiofilmQ does know and display to you is some of the metadata. And it's important that when you import files into BiofilmQ that you check this metadata, because sometimes when you have edited files after exporting them from your microscope, it can sort of screw up the metadata in a way that BiofilmQ is unable to read it. That doesn't mean that this data is useless with BiofilmQ. It just means that you'll have to use a different way of importing. And I'll talk about that in a second. For now, what you can see here is that in this particular file, we have one position. This position has a Z-stack of 31 images of dimension 1024 by 1024, 2 channels and 1 time point. So you check this information, you check that it's all correct, and then what you can decide is whether you want to have separate folders for each position during the import or not. And this basically is relevant, especially if you have a time series and several positions. Then you always want to separate them. Otherwise, it all ends up in one folder, which is going to be tricky. And also, if you have several positions and you check this box here, the output will be in a way that allows you to, for example, perform batch processing easier. What you would do once you have decided whether you want to check this checkbox or not, you would just press on import, and that would be it. BiofilmQ would import all these files, and then it would allow you to open a directory. And I'm not going to do this now for time reasons. I'm just going to show you what this would look like. In our case, we would end up here. So this would create a folder that has the same name as sort of my original ND2 file. And if I go in there, I will then have sort of like the typical BiofilmQ view where I can see the image of the stacks and everything. So this is one way to do it. The other way, and that is especially relevant if you find that BiofilmQ has trouble importing your data, for example, because you modified it later on and now the metadata cannot be read by BiofilmQ properly. What you can do then is you can export your ND2 file into TIFF files in a software that can open this file. So for example, for ND2 files, there is NIS Viewer, which is free, and you can just download it, and you can then basically take this image that you have taken and separate it into individual TIFFs. This is what I've done in this folder here. So I'm also not going to show this in detail because we have this online in tutorials as well. But basically you can generate these files here. So these are all individual TIFF files that have, again, the name of your file, then the position, the Z-stack position, and the channel, kind of indicated with this X, Y, Z, and C. And this is what you can use to import into BiofilmQ using the custom TIFF import. We also have tutorials on that. To do that, you would basically just use this directory as an input up here and then kind of walk through. What I did for today is I wanted to be smart. So I decided we're going to work with 2-dimensional data. So what I did is I went into this folder where I have all my tips, and then I selected one sec that seemed to be pretty much in good focus. And I dropped it into a folder where I basically just have this one image, and now it's just these two channels. And then I imported it into BiofilmQ, and this was the results basically in here. So we're going to navigate there. The reason why I chose to do this in 2D today is because it's much faster. And that means we can do things live, and I don't have to say, oh, I prepared something here, I prepared something there, but you can actually see it happen, which I think is a little bit nicer. So we're going to look at this particular image today for the majority of the tutorial. And what this shows here is that we have a mixture of two strains that have different colors in which they fluoresce, inoculated on an agar plate, and then grown over a span of time. I don't know how much, because I didn't do this experiment. But essentially, it's kind of like the colony grows alpha. This is like, I guess, a standard competition experiment where you want to see which strain sort of dominates in the outer region. And in this particular case, from looking at it, I wouldn't really be able to tell if there is a strain that dominates, maybe slightly, but I'm not sure. So this is something that you might want to analyze with BiofilmQ. The way that we do this now today is with merging. And I think this was, for this particular example, it would also really be the best, or maybe the only way to do it. What I'm looking at here right now is the merged view. I can also look at it in sort of the unmerged view. What this basically just does is now I can see the image in my channel 1. And if I click on display merge view, it's going to show me channel 1 in one color and channel 2 in a different color. So channel 1 is in this case represented by red color. So this is just so that I know what my colors, what my channels look like combined. This is especially, of course, relevant if you're thinking about merging. And now coming back to the reason why we perform merging, in this particular case, you can see that basically every area in this image is either red or green, but I don't have a channel that has sort of the entire colony fluorescent so that I could segment it. So if I segment the first channel, I'm going to get all of the cells that are in the regions that are fluorescent here. If I'm going to do the second channel, I'm going to have sort of a complement of that. But if I wanted to analyze the entire community, I don't have a way to do that unless I sort of combine the information from both channels. And that's what merging does. So we're going to first segment these channels now. And here I'm going to choose a very basic segmentation. I uncheck the top hat filter because this is mainly more for single cell like kind of calculations. I'm only denoising very slightly, and I chose also thresholding with a relatively low sensitivity. So basically what I did was, of course, I started with a standard sensitivity of 1, and then I found that so if I put 1 here, I felt like it was going to cut off too much. So I chose 0.6 here, but we could put anything else also, depending on what you want to see. And we will see there's quite a little bit of overlap between the channels when we choose 0.6, but for the purpose of today, I'm just going to go with that. And then for the object declumping, I chose a relatively small cube size of 5 pixels. In this case, it's reasonable because we have a 2D image, which means that everything's going to happen a lot faster. Usually what I recommend is 5 is okay, but to not go below 5 pixels if you don't really have to for the cube size, simply because it's going to take forever. But yeah, in 2 dimensions, it's a lot faster. So 5 pixels is perfectly fine here. And you could go even lower without having to wait forever. So now I'm performing this segmentation, and you can see it is really fast, mainly because we have a 2D image. And I'm just going to go to channel 1, keep all of my settings the same, because I want to have it somewhat comparable. And then I'm just going to do the segmentation. You can see that the settings here, that basically were taken over to the other channel as well. So I can segment my channel 1 as well, and then I have segmentation for both channels, which is great. Now comes.
Hannah, can I ask you just quickly? So would you always aim to have the same segmentation settings if you have multiple channels? I mean, if one channel, for example, is not so bright as the other one, wouldn't you use a different sensitivity, for example?
Yeah, absolutely. So in this case, I used the same ones because the intensities were comparable. But if basically you just want a good segmentation for all channels, and this can mean very different settings for different channels. So here it's not at all, it doesn't at all have to be the same. The only thing that has to be the same is the cube size. Everything else you should adapt to what your specific channel looks like. Of course, if you have cells that are maybe from the same species but different colors, you would aim to have them sort of represented like as the same size. So of course, if you perform different type of filtering and different type of thresholding, it sort of changes the final size of your segmented cell, right? Because it becomes bigger if you lower the threshold. So you would aim to have a consistent segmentation. And I think that's probably the most important thing, that sort of the segmentation between channels is consistent so that your cells are represented sort of in the same way, if that makes sense, I hope.
Yeah, yes, cool.
Okay, so now let's go to the merging. So the merging is a little bit hidden down here. You can see that we have a merge and a transfer. I'm not going to talk about the transfer today, but just so you know what it is, the transfer of a segmentation is an interesting thing where you can basically move a segmentation from one channel to another channel. The question is, why would you ever do that? And the answer is basically, or in my view, basically, if you want to, originally we had it implemented when we had the label image, so that you would like segment the label image or sort of like a binary image. If you have a channel that represents a binary image of your biofilm, you would be able to segment this biofilm in the binary image and then transfer the segmentation to your main channel. But actually also the data set that we work in with our other sample data set, where we have one biofilm that has a certain color and the other one doesn't, transferring the segmentation can sometimes be helpful in order to be able to work. It's different to explain, but I guess that working with a binary image, for example, is the best example when you would want to use this. But in general, this is just a feature that exists and you should use it responsibly. But I wanted to tell you that this is also down here. But coming back to the merging, you can merge multiple channels into one. So if I have 3 channels, I could just put 2,3 here or 4, however many I have, and it's going to merge them all into the same channel. So it's not limited to 2 channels at a time. And when I press this button merge, one thing I need to have is I need to have a segmentation already for all of the channels that I want to merge, as well as the channel that I merge into. So in this case, if I only had segmentation for channel 1, for example, it would give me an error. When you merge, you will receive basically this message here. And what this means is that the segmentation in BiofilmQ is saved in this folder called data. So this is the folder where my images are in. And I have this data folder. And in this data folder, I have 2 files that represent the segmentation of channel 1 and channel 2. And when we perform merging, these 2 segmentations, like prior to the merge, are saved as a backup, so that in case that you don't like your merging, you can go back without having to resegment your data. So in this non-merged data file here, I now have the original files. And if I were to copy these back into my data folder, replacing these files, I would go back to the previous stage that I had before merging, which can be useful because sometimes you find that merging wasn't what you wanted to do, and then you want to go back. So this is basically just a backup of your data. It also contains all of the parameters that you would have calculated prior, because merging will also remove any parameters that are not overlapping between the channels. So usually what you would want to do, if you know you're going to merge your data, you don't calculate any properties before you merge, because they are going to be lost in some cases. So now the merging is complete. Let's have a look at what it looks like. And in BiofilmQ, there are, of course, several ways that you can look at your data. One of the most maybe commonly used ones, or that are quite useful, is to have this overlay. So maybe I will start with that. And it says me no file selected. If you ever get this error, it usually means that you forgot to select the file over here. Because right now, of course, I only have one file, but usually you have a list. And then if you click on overlay, BiofilmQ doesn't know which one it's going to use. So now that I selected a file, it actually can perform the overlay. Again, this is fast because I have a 2D image, but if you had a 3D image, this could be fairly slow. So this, I usually don't use the overlay myself, because to me, it's just way too slow. What the overlay allows you to see is what your segmentation looks like, but also what your original intensities look like. In this particular case, I see the intensity of channel 1 because I applied it to channel 1, but you can already see in this, all of this red area here is basically part of the segmented biofilm. And you can see the cubes, that they're very small. Sometimes you can see sort of gaps in here. This is sort of a rendering issue. It's not that there are no cubes there. It's just that like the the way that the screen is showing me the data is just like a little bit inconsistent. But basically what you could see here is that which areas are segmented well. And then you can see that, for example, we have a little bit of a roughness out here, which makes sense because some of the areas, especially outside, are a little bit darker. Now you could, for example, go back and think about, well, do I maybe want to lower my threshold so that I get the entirety of the biofilm all the way to down here? Or am I happy with how this is? What you can also see already here is that after the merging, and maybe I should have shown you what it looks like prior to merging, but after the merging, even the areas that are dark in channel 1 have cubes. And this is because these cubes were present in channel 2, meaning that in channel 2, when we merged the files, they were basically moved over to channel 1. What I can show you, I guess, is I can show you in channel 2, because channel 2 still contains its original segmentation because it wasn't overwritten. In channel 2, if we do the overlay, we should be able to see that we have areas where we don't have any cells in channel 2, and these areas also don't have cubes. And this is exactly what we see. We see that this cubed area, which kind of to us appears red, so we can fairly easily see which part is segmented, that this is only the area that is present in channel 2. So this is what it would look like if you do sort of a normal segmentation. And then after merging, it looks like what I've just shown you, where everything is red. So the merging seems to have worked. And for now, I'm going to be happy with it. And I'm going to show you another way to look at your data, which is something that I do a lot more, which is to load the segmentation results down here. Because this allows you to look at your data already at some of the properties that you have calculated. And this is one form of visualization that I use a lot, because it can basically very quickly give me an overview of what I calculated, if it's like reasonable or not. So here we have a list of all of the properties that are calculated by BiofilmQ. And it includes these properties here: cube overlap, 3D, relative abundance, channel 1, and relative abundance, channel 2. And this is basically exactly what the name would indicate. If I look at abundance of channel 1 and I go to this auto view, it's going to open an auto view where every cube is colored in a different color according to this particular property. Right now, we can see that a lot of cubes are yellow, and this means, if we look at the color map, that in these particular cubes, 100% of the cube is filled with channel 1, basically. So 100% of the cube is assigned as the cell in channel 1. We can see there are some regions where the cubes are not yellow, where we have all the way down to 0. In this case, 0 is represented by black, basically relative abundance. And these would be the cubes that are sort of at the boundary between these two regions in my biofilm, the green and the red one. Or when it's black, then this is where there was no presence of red cells at all. And this would be then the green cells. But there are cubes in here. We just saw in the overlay that there are cubes in here, and we can also see it if we look at a different property, such as volume, that there are cubes present in these areas. And here you can see the volume of most cubes is really the same, just because they're completely filled. But you can see this area, it is segmented. It is part of like the merged segmentation. It just appears black here because there is no red cell in there. We have someone who has a question. Would you like to ask it out loud?
Hi, yeah, sorry. I'm not sure if I missed something, but after you merged the channels, after you segmented and then merged the channels, how did you get the parameters? Because you did you actually go in and select the parameters and ask it to calculate?
No, I did not. Merging already calculates these specific parameters.
Right.
Whenever you perform a segmentation, there are some parameters that are immediately calculated, such as the centroid, the bounding box, center coordinate, and also volume. And then merging specifically also adds these three: the overlap and the abundances. And anything in addition to that, I would calculate in parameter calculation.
Okay, great. Thank you.
So yeah, and that's exactly what we're going to do right now. We can think about what kind of parameters we want to calculate. And in our case, it's what we want to look at in the end in our hypothetical competition experiment is we would want to look at the abundance of the strains relative to where they are located in the biofilm, because that's basically our time. So what we're going to do is we're going to calculate the distance to the center of the biofilm. And this is actually, for now, the only thing I'm going to calculate, which is also going to be fairly quick. So we can just kind of wait for it quickly. Later on, we're also going to calculate other properties, but we'll get there when we get there. For now, we're going to wait until the property is calculated, and then we're also going to look at it and then move on to the visualization to see if we can already kind of make sense of our results a little bit. So I can load the segmentation now. And yes, it appeared. So now we can see we have two new properties, distance to biofilm center and distance to biofilm center at substrate. The difference is mainly that basically, in the second case, the distance to the biofilm center would be projected to the substrate. In our case, because we have a 2D biofilm, that is going to be exactly the same. If we look at what it looks like, we can also see very beautifully just how it changes from inside to outside. And you can see here that we really have very small cube sizes because it almost looks like it's continuous, whereas actually we have cubes in there. Maybe it's also interesting to see, now we can actually also see the size of our biofilm. It's like about a millimeter, 1.5 millimeters in radius, so about 3 millimeters in diameter. It's actually quite big. So yeah, now that we have that, let's have a look at the visualization part. And moving here, let's see if we can load the data. Again, this should be relatively fast because we have a two-dimensional data set. It's not very large. And now the first thing that I want to ask essentially as a question of my experiment is, if I move from inside to outside and I look at the relative abundance sort of in this, yeah, well, let's say ring going outside, is it going to change and how is it going to change? How do I do that? We have a bunch of tutorials also specifically for the visualization. So I'm just going to quickly say that we have different properties or different types of plots that you can perform. Ranging from a histogram, which would be fairly simple, all the way to a, we call it 4D because we have X, Y, Z plus color scatter plot, but you can also do these chymographs that we have in a lot of papers from the lab. And then in the parameter selection area, you can always choose between single object and global biofilm parameters. So single object parameters are the ones we see here. These are the ones that we also were able to look at in this view before, down here. But we also have global biofilm properties, and depending on what you calculated, these can be something like the biofilm overall size. But you can see that actually for every single or for every single object property, we also have this little plus here, and this is kind of like a statistical summary. And you see it's quite a lot, but in principle, you can, for example, have for the whole biofilm, what is the maximal volume of a cube? Or if I look at, for example, the overlap, what would be the maximal overlap value? So these are global biofilm parameters, which means that we have one value for the whole image. And of course, visualizing that, if you don't have a time series or if you don't have different positions, is a little bit boring because it's just going to be one number. And if you wanted to know this number, you could actually look it up in this table here, which is quite extensive. So we're not going to look it up. If you did want to look at these individually, I would recommend that you do an export into a CSV file. But this is also something that we have tutorials on, and I'm not going into that today. What we are going to look at is we want to look at single object parameters, and we want to perform a plot that we call 1.5D histogram, which is like a very interesting way to see it, I guess. Why is it 1.5D? I don't know. I guess at some point we decided to call it this way. What it actually is basically one parameter resolved by another. So we basically do a binning based on one parameter, and then the other parameter is going to be our y-axis. This is very useful to see if we have any correlation between different properties. And what we want to see today is we want to have the x-axis as a distance to the biofilm center, which sort of represents our time. And then the y-axis is going to be, for example, relative abundance. We can look at this, and now let's have a look at what all of these weird things mean. Well, first of all, we have this thing which is called automatic range, I think. And then over here, you can check true range, which allows you to set kind of the boundaries of your axis. And in our particular case, this is quite useful because then we don't need to worry so much about what do we want the axis to be, sort of like we would need to look up how big is the biofilm and everything. Just basically just the axis range. So we just set it to 1 to 99, and this is probably going to be fine. We can also set it to min-max. What's really important back here is that we think about the number of bins, because essentially what this does is it's going to bin our values according to the distance to the biofilm center. So if we choose too many bins, for example, they might be very small and might not contain a lot of data points, which might make it very noisy. I typically like to go for something between 10 and 20 bins, but it really depends on your data set. So this is something to think about. What is incredibly important with the bins to realize is that if you have a spatial measure and you have a cube size, then choosing a bin size that will result in bins that are smaller than your cube size never makes sense, because it's basically only going to have one layer of cubes assigned to it. So this number of bins, typically if you go for something like maybe 15 or even 10, you're like in a good range. Often you also don't need a lot more. If you look at this, so I'm not going to, you can save files. I mean, I guess we can do it once. Usually I don't save them also because it takes time, but this is going to perform a plot. And somehow it does, let's see. I don't know why, somehow it doesn't show up on my screen, even though it's done. Where's this? It showed up on my other screen. Well, there it is. So basically this is the abundance of channel 1 across sort of our time axis. And just to have a relation to that, what I'm going to do is I'm going to plot the abundance of channel 2 into the same figure. So this is also something that some people are not aware exists, but it's actually quite useful to add a plot to the same figure. And if we do that, we can sort of see how both of the strains are sort of growing, how we have already from the start a higher abundance of the strain of channel 1. And then we have sort of some variation in there. So this would be one measure that we could do in order to look at this experiment. But if I look at this, I'm still not sure if like one strain really outcompetes the other. It doesn't look like it. But depending on what the data would look like, I might want to really be able to quantify this like properly. And one thing that I would like to do here is I would like to be able to kind of have the same starting point. So one strain starts at like 45, the other one starts at 70%. And that tells me that from the start, I already have a difference between the abundance of strains, which means that I would need to take that into account. So now maybe going back to what is actually the question that I want to ask and how do I want to compare these strains? Well, what I want to have is I want to kind of have something like a growth curve even of these strains, and I would like to compare it to each other. How could I do that? Well, I could maybe try to sum up the biomass along this line and then have a look at how it sort of arranges or how it increases over time. And this is something that I can do if I apply a custom script to the plot. What I would actually want to do if I think about it is I would want to take the volume of all of the cubes of a certain color and sum them up over time. So let's first start to think about what it means to sum up the volume of the cubes of a certain color. And this is where the filtering gating comes in. So I'm going to keep distance to biofilm center as my x-axis, but as a y-axis, what I'm going to do is I'm going to switch to volume of a cube. And instead of looking at the mean, and this is something we haven't discussed before, there is a certain method associated with the histogram. Of course, if you bin everything, you can take a mean, but you could also just sum it all up. So now what it's going to do is it's going to take the distance to biofilm center axis, kind of chop it into pieces. And that's going to ask in this particular range, all of my cubes that fall in there, I can just sum them all up. And this means that I get like a combined volume of these rings that are going outside. And if I want to now select either cubes that are red or cubes that are green, what I can do is I can filter and only take cubes into account that have a certain property, namely, for example, that the relative abundance is greater than 50% in channel 1. If I do that, I'm pretty sure to include most of the cubes that are predominantly red, and I'm going to exclude most of the cubes that are predominantly green. And this way, I should be able to see how it develops over time. So let's do that for now and see what it looks like. And again, unfortunately, the figure appears on the wrong screen, but we're okay with it. So now what we see is we see sort of this increase in time, but it's still not the same as having a growth curve, because what we see is essentially how the biomass in every ring around this region here So if I would take ring and ring and ring, I would see how the biomass within the ring is, but not actually how it accumulates. If I want to have the accumulated biomass over time, I would sort of need to sum these data points up. And this is something that I can do actually fairly easily in BiofilmQ by applying a custom script on the plot. And it's always very daunting to apply like custom scripts or to do any scripting. But I do really want to encourage that you kind of look at these possibilities, because it's actually, it doesn't require too much programming knowledge. And we also have included already some kind of templates where you can see examples for it. So what could I do here? And if I go on browse, you can see actually where in your BiofilmQ path you would need to look. So here it tells me somewhere, and like I can look at the whole path in my BiofilmQ, in my includes biofilm analysis and custom scripts. This is where example scripts are. So there is an example script to modify a plot. We can have a look at this example script by going into MATLAB, and I think I have to close this first. Yes. By going into MATLAB, and of course I already have it open, but so it said includes, then in, I think, biofilm analysis, custom scripts, exactly. So there's this modify plot example script, which we can open. And it's actually also a fairly simple script. We can see that here it's just a line that was added to the plot. I did already prepare a script to sum up our values because I wanted to have things running a little bit more smoothly today. But I'm going to walk you through how I created this. So first of all, I can get all of my X data points just from this particular command. So in the future, if you ever want to use a custom script, you know this is the command that you can use. And now what I basically just do, I take my X values. I don't want to change anything about the X axis. And for Y, I'm going to use this a function called sum, which is the cumulative sum. So I can look it up with MATLAB, which surprisingly doesn't work. Yes, it just, again, works on the wrong screen. So with a stock command, you can look at different functions. And here it's basically, it just returns the cumulative sum of A. So that's great. This is going to give me the cumulative sum, and then I can create a new figure where I can plot this. So I'm going to do this now and apply it. And I will, for a moment, I will comment out this bottom part because that comes later. So let's have a look at what happens when we do this. So we're going to do the same plot. We select this file that we just wrote, which really is fairly simple. The only thing is that it does, it applies this cumulative sum before plotting again. So all of this is just plotting. And in fact, if you only had this one line, it would give you a plot. The only thing is I'm going to do it like I'm going to open a new figure, then I want to have a box, I want to have a label, but all of these things are aesthetics. The only command that you would need is this command. And actually, this is also something we don't need yet, but we're going to talk about in a second. So let's do that and see what happens. And I'm going to get a plot which appears in the wrong window as always. And this is what it looks like. So now we have accumulated biomass over time, and now we can actually see something that looks a little bit more like that. So this is great. We did this for channel 1. What if we want to do this for channel 2? For channel 2, we basically just change this. And what would happen if I now press plot is it would give me the same type of plot, but unfortunately it would be in a separate window. So I'm going to show you another trick that is specific for MATLAB, is really useful, which is breakpoints. A lot of people that already do programming might be familiar with breakpoints, but for those who are not, breakpoints are a game changer in any kind of programming. Basically, you just put like, you click on a certain line, and then when I run my command, which would be the same as before, it stops in that line. And this means that I can now modify and change things that are happening in here. I can in fact, and this is my workspace in MATLAB. Don't be intimidated by that. It's your friend. It's an amazing feature that we have workspaces when we program. I can look at this X. So X is something that I introduced here, and I can actually, if I double click on it, I can see the values that are in here. So this is great. This is why debugging is amazing. So now, right now, it has stopped in this line. And what I can do is I can now select this previous image that we had of our channel 1. And because of the hold on command, which basically tells MATLAB that it's going to plot it in the same figure, if I now press play again, our second plot should appear in the same window. So now I get the distance. So now I get both channels again, channel 1 in blue and channel 2 in orange. And they are plotted sort of in the same figure. And I can sort of see for both of them what the growth curve looks like. This brings me a little bit closer to the question, which strain outcompetes which, but I still have this problem that in my very first time point, I already have a mismatch. And it might not look like much down here, but actually for values so small as the ones here, it can mean a big deal, which is why we're going to make one more modification to our script. And this is we want to have a normalized biomass. And what I do here is I normalize it to the first value. So right now I have y, and now I'm introducing this additional variable y normalized, where I take the whole vector of y and I divide it. And the reason why before the division there's this little point is because we have a vector that we divide rather than single numbers. And I divide it by y of 1, which is the very first entry of y. So y is a vector, y of 1 is the first entry, which means that essentially what this does in the end is it's going to divide every single point in here by the value of the first point. So the first point should actually have value 1 after we do this. Let's try what happens when we perform this. And here I decided that I just want to plot things twice. So I'm going to plot the original one, and then I also want to plot the normalized one just so that we have a comparison. And I'm going to close all of my previous figures because, as you can see, if I go down here, there's a bunch of figures open and it's going to confuse me. So I'm just going to close them all, which is another thing in MATLAB that can be useful if you have too many windows open. All right, so let's start again with channel 1. And we are going to plot it. Let's see if we have everything right. This looks fine. We will have several figures that open in the wrong window as always, but that's okay. This is figure 2, this is figure 3. Figure 1 actually was the original before we even apply the script. That was the one we don't have the cumulative sum, but this is not so interesting for us. And here we can now, if we look at this first data point, we see that it's 1. So this is now the normalized curve. So let's do the same thing again for channel 2. And I'm going to have my little breakpoints in here. And I'm going to have my first breakpoint in line number 14. And I'm going to comment. And commenting is done by putting this percentage sign. I'm going to comment this figure command because figure opens a new figure. I don't want to open a new figure. I want to add to an existing figure. I'm going to have 2 breakpoints, one here and one here. And the reason why I have them is because I want to run the script. And then when it reaches the point, I want to select the figure in which I want my data to appear. So this is the first figure from my channel 1 where I don't have the normalization. So I'm going to press continue. And now I'm going to select the second figure where I have the normalization. So this is y is 1. I'm going to again continue. And now what I should have as a final result is 2 figures where we can compare next to each other what happens if we have our 2 strains growing together in this unnormalized form. How do they grow over time? And this is the distance by from center, but in fact, it's sort of time. And what happens when we grow them, when we normalize this. And now in the normalized case, we can see that, sure, there might be a little bit of the blue strain outcompeting the red one, but actually it's really not that clear. And probably if we went and we did replicates and we did error bars, we might or might not see that this is significant. And this is one way that you can look at this type of data. So now what I have hopefully shown you for until now is a little bit about how we do the merging, how we understand the properties that come out of merging, and how we can utilize this visualization with a custom script to kind of go a little bit deeper into our data and do some things that are kind of specific to our data set. Too specific for BiofilmQ to already have a function for it, but with very little means we can make a function. I do want to also show you something else, and I think here I'm just going to talk about it without going into too much detail because we have 15 minutes left. I still want to show a little bit about the batch processing. I also want to have time for questions. But I do want to show you that we have also custom parameters in the main parameter calculation. And there are two types. One of them is, again, a user-defined MATLAB script, which means that here you can see the file. There's also a template. And we don't have time for that, but I did also prepare one for today. But essentially what you get in here, and maybe I'm going to just run it with a breakpoint to show you what this would look like, similar to what I showed you before. So what you would do is, if you wanted to do that, you would select a certain script, again by browse. In this case, I think the one that I chose was this one here. Make sure that you check it, and then you can click on calculate, and it should end up in our breakpoint here. So what do I have as sort of properties to work with if I have a custom script? I have this variable called object. If you open it, it might look, again, a little bit overwhelming. We have a variety of different things, but you care about only a few of them. One of them is measurement fields. These are all of the properties that we have, and we can access them. And the way that we access them is by doing this. So if you have this one basically line here, objects dot stats dot, and then comes your name, what comes out of this, you can sort of see it down here, is a vector where we have for every single cube this particular value. Now what I can do, and what I did in the script, for example, was I decided I wanted to divide not by the first time point, or not by the first kind of plot point, as we did before, but I had prepared like sort of another script where we would divide by the central area, and we would define a parameter that would tell us what is our cutoff distance in micrometer. And here we said, okay, it's 400 micrometer. So everything within 400 micrometer we call sort of the center, which is our inoculation site. And this is going to be the basis for normalizing our data. And what I did here in particular is I would first define which cubes are associated with the central part. And then I would do an operation where I multiply the volume of each cube with its relative abundance in each channel, but only do that for the central cubes. And now this, I'm not going into detail of what, this might again look a little bit overwhelming. I just want to show you that this is how you can access your data in BiofilmQ in MATLAB if you want to do a custom script. And then if you want to set properties, you can do this thing here, and this is also shown up here. So you would be able to copy paste this. In fact, I copy pasted this. This is how you set new properties. So if I run the script and I run through it with it, I will have two new properties, which are called biomass relative channel 1 and biomass relative channel 2. And I can also set global properties here. So I can just continue this. And then once it's done, I would be able to see these two additional properties. But a lot of people are not very familiar or comfortable with programming, which is why we have, for this particular case, for the parameter calculation, we also have the possibility that you can define a parameter within the GUI, within the user interface, which is this part here. And this might be more interesting for some of you. So actually here, I did the exact same thing that I did in the script. I just kind of wrote it as an equation. And maybe we can start with something simpler. So I can have something which is just like my parameter. And then maybe I want to, I don't know, divide the relative abundances by each other. Who knows? Maybe that's what I want to do. The way that I do this is I select a property, I add it, then I add like the operator, which in this case would just be divide them, and I would add the second property. I can test if this would work, which is great. In this case, it does work. If I had something like a mismatch of, for example, I have something at the end and I haven't opened it at the start. So if I have an invalid formula, it's going to give me the error message, and then I sort of have to figure out what the error message means, but at least I know it's not going to work, and I know I don't have to go through the process of calculating it. And up here, you can see what are the different operators you can use to combine features. So this can be a division, multiplication, plus, minus, but you can also use logical operators. So you could also say, I want to have a binary kind of property that just tells me if this cube has a relative abundance of greater than 50. Or maybe you want to say, oof, if there's a lot of overlap, I actually don't want this cube to use this cube. So I'm going to say, I define everything with an overlap of greater than, I don't know, 20% as a parameter, and it's going to be a binary parameter, and I can use this for filtering later. For example, in the visualization, I could use the filter and kind of exclude these. So these are all ways in which we can define new parameters that are going to later on help us kind of work with our data in a more customized way. And it's always great if you can do programming and if you have MATLAB, but of course not everybody wants to do it. Not everybody has access to MATLAB license. And in this case, at least you have this option here, which already gives you a lot of freedom to define new parameters. And maybe here we can quickly check that the two parameters that we just calculated from this MATLAB script appeared. And in fact, yeah, they're down here. And if we do this and we check this option now and we do another parameter calculation, it should also appear. So this is basically just how easy it is to define your own parameters from existing ones. All right, I will spend about 5 more minutes talking about the batch processing, which I think is also something that can be very useful if you have a lot of data. The batch processing is a little bit hidden in this part up here. And let's just very quickly check that my parameter actually got calculated. Yeah, there it is. That's great. All right, so the batch processing is hidden in the process shortcuts up here. There are two types, simple and advanced batch processing, but actually the advanced batch processing is just sort of a way to automatize the simple batch processing even further. The simple batch processing consists of selecting tasks and then basically just running it. The tasks that you can see here have little check marks next to them. If I click on it, unfortunately it closes, but you can see that the check mark disappeared. If I want to not do a segmentation, I'm just going to uncheck this. So here you can select which tasks you want to do. Registering images means that you align them. Segmentation is something that you know already. Calculate cell parameters, so basically pressing this particular button here. Then there's tracking, creating visualization files. This is all in the export area. So say, for example, we wanted to just do a segmentation and a parameter calculation, but we didn't want to track any cells. We didn't want to create any visualization files. So basically, we just want to have a fairly simple pipeline. What this is going to do is, and you can also select and unselect all. What this is going to do is it's going to basically apply these two steps, one after the other, with the parameters that we set. So we'll set everything up, we'll set all of the parameters, and then it's going to run this once we hit perform select tasks. But now it says on all experiment folders. What does that mean? Well, in our case, what it basically does is BiofilmQ always expects that we have a certain type of directory. If you import a ND2 file that has a lot of positions into BiofilmQ, it will create, and I talked about this at the start, you can have the option to create one folder for every single position. And then BiofilmQ will be able to identify, oh, these are all sort of same type of folders. I can run my batch processing on all of these folders at once. So you will basically have a folder structure where you have a lot of folders with your data in one parent folder. And just for one of them, you set everything up, and then you just say perform selected tasks on all experiment folders, and it's going to do it for all of them. So this can save you a lot of time. And here it actually says it up here. It says size of current folder, blah, 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 and number of similar experiment folders. And this would be sort of the sister directories. So if I were to apply batch processing, it wouldn't just apply this on this one folder, but it would apply this on all of the folders that are in the same directory. So it would apply it on all of these. These are the 5 folders that BiofilmQ is talking about. Of course, if it were to open them, it would find that actually some of them don't contain data suitable for BiofilmQ. So we would get a ton of errors. But in principle, you would set it up in a way that all of them are set up as being a position, for example. Now, one thing that is important to know is what about the settings? The settings of basically everything that is set in the GUI, the settings are saved as this parameter file. So whenever you open any kind of folder in BiofilmQ, it's also automatically going to create this parameters file. If I were to open this in MATLAB, and I just looked at it, so it's called params now. It basically contains this. This is all of the information that you have input into the GUI. All of the text fields, all of the checkboxes, all of this is in here. So basically, when MATLAB opens a folder, it looks in this parameter file and uses it basically to pre-check all of the settings that you had last time. The best way, if you want to take the settings from one folder and move it to another folder, is to just take this parameter file, go to the other folder, and place it in there, and replace it. I forgot to replace it, but and replace it. And basically, if you had sister directories, you could just take one parameter, you would set everything up for one folder, place it in all of the other folders, this parameter file, and then you would hit this simple batch processing. So that's great. Now, what is advanced batch processing? That actually is already quite a lot to do. What can you do with advanced that you can't do with the other one? Well, in this case, you have more options. You have the option, for example, which folders you actually want to do. So you can select only a handful of folders instead of all of them. You have the choice if you want to use a specific parameter set where you would select, for example, the parameter set that I have right here. And then you can see it sort of has this path here. So it would use this parameter file for all of the folders. And then there is something called a batch file. And this is the one thing that you need for advanced batch processing, which again brings you back to needing MATLAB, but it's also not magic. So let's have a look at that. If you go to batch file and you go to browse, it's going to automatically go to the, actually it doesn't go to the directory. I thought it would go to the directory where the batch files are, but we can find them anyway, right? Let's see. Can I actually find them? It would probably be with object processing, batch processing. Well, this is a little bit slow, so I'm going to look for it. Probably should have prepared. So this is, by the way, again, perfect thing to work with MATLAB. If you want to find something, and you press Control upper arrow, not the upper arrow, but the arrow that makes everything happen. Sorry. and F, you get this view here where you can look for specific text. And I know that a lot of the batch processing is has batch underscore. And interestingly, the ones that I'm looking for are not among them. That is strange. And you can say, I only want to include files that are MATLAB files. Interesting. So it looks like we actually don't have example files included there, which is unfortunate. In principle, and maybe I'll check that we do upload these, which means that I also don't actually have them downloaded right here. But in principle, these files contain, or these MATLAB files, simply contain the same thing that is also written in these shortcuts with the same tasks. And you also just select which ones you want to use. It's just sort of more in a file format or in a script format than in this a little bit more complicated and like you have to click a lot of times format that we have here. But the main advantage of batch processing is that you can select which folders you want to use for, and you could even select like you could go several current folders upwards in order to perform batch processing. So yeah, this actually means also that we're perfectly out of time. I am anyways going to stay here for questions though. I think I went through pretty much everything that I wanted to show you. I hope that you learned something new. And I hope that, yeah, you will keep working with BiofilmQ and keep connecting with us through the forum, because that is the one place where you have the best chances of us answering, because it's public, so we want to answer it. Now, we also answer email. But so the image.sc forum that you're probably familiar with, but I'm just going to bring it up anyway. Just in case that you haven't seen it yet. This is the best place to contact us. You can always write us an email, sort of like us personally, or our biofilmq@gmail address. But this is a place where we typically answer. As you can see, somebody just posted something 8 hours ago, and Niklas already replied. I also already replied, interesting, but not within the last 8 hours. But yeah, this is basically, we check this every other day or so to make sure that these questions are answered quickly. But right now you have the chance to ask me right here and then. So take the chance. I'll be here for as long as it takes, but not more than an hour. Thanks for joining.